All right, we're going to go ahead and work our way through the circuits test here. It should be noted there were a few different versions of this, so your numbers and exact answers might be slightly different, although if you log back on, you should be able to see the correct answers. But this at least will go through how you do these problems. All right. So for this first one, we have a laptop with a voltage of 12 volts and a power of 30 watts, and we first want to find the current. So for this, we're going to say power equals voltage multiplied by current. So I can say 30 equals 12 times I. I'm of course going to divide both sides by 12 here. And I end up getting that my current here is going to be 2.5 amps. For the next one was the effective resistance of the laptop. So for that, I'm going to go back to Ohm's law and say V equals IR. So my voltage here is 12. That's going to be equal to my current, which is 2.5, multiplied by my resistance. So when I go ahead and divide both sides by 2.5, I end up getting that my resistance here is going to be 4.8 ohms, which is the horseshoe symbol. While using the computer for 15 minutes, we want to know how much charge runs through the laptop. So I know the current, and I can relate current to charge through this equation that current is just defined as charge per time, delta Q over T. I do, though, need to do a quick conversion here because 15 minutes is not the unit I want. I want that time in seconds, so I'm first going to say 1 minute is 60 seconds. When I multiply that out, I get 900 seconds is my time. And so then I can say my current, which was 2.5, is equal to the amount of charge over my time of 900 seconds. And so I would cross multiply here, and I'm going to end up finding that delta Q equals 2.5 times 900, which gives me an answer here of 2,250, and the units are going to be coulombs, 2,250 coulombs for that answer. For the last one, when the computer is used for 15 minutes, how much energy is used? So similar equation here, except this one relates power and energy. Power is work, or the change in energy over time. Same idea because work is the change in energy. So I'm going to take that power that I had from before, which was the 30 watts. That's going to be equal to the change in energy over my time, which I'm still going to have in seconds, so 900 seconds. We cross multiply once again, and I get that my change in energy is going to be 30 times 900, which gives me a change in energy here of 27,000, and the units are going to be joules because those are the units for energy. Moving on, we have a conceptual question here. So we have three circuits, A, B, and C. And we want to know which circuit will have the most total current, meaning the current running through the battery. So if I think about what I know with Ohm's law, V equals IR, the voltages are all the same. So what ends up happening is in order to get more current, what I need is less resistance. Okay, so less resistance ultimately leads to more current. We see if this number drops, this number will increase. And so I want the circuit that has the least amount of resistance. Circuit C is going to have the least resistance because we added resistors in parallel. And when we add resistors in parallel, that decreases the total resistance. Remember, that's that idea that it creates more possible pathways. Instead of just having one pathway like A and B do, C has two separate pathways. Each one only has one bulb on it. And so that means that circuit C will actually have the most current running through it. For the next part, I want to think about which circuit has the light bulbs with the most voltage across them. So the battery has some voltage here, V. And if I think about these three circuits, okay, I know that every loop must lose the voltage of the battery. So circuit A, the only bulb on that circuit is the single bulb in there, so it loses all of the voltage across that bulb. With B, all right, there's actually two bulbs, so each one is going to get half that voltage, whatever it is. And then with C, it's actually two separate loops. So even though there are two bulbs, each one gets the full voltage of the battery, okay, because both of them are on their own loop, whereas in B, they're on the same loop, and so they have to share the voltage. So the correct answer would be A and C, okay, are going to get the most. They're going to be tied. All right, so for this next problem, we have a series circuit, we're told. So it's a 9-volt battery here, and we have a 2-ohm resistor connected in series to a 4-ohm resistor. And so what we're going to do is we're going to first find the total resistance of this just by adding up those two resistors. So the total resistance is going to be 2 plus 4, which gives us 6 ohms. From there, we can go ahead and figure out the current running through the circuit using Ohm's law. So I'm going to say V equals IR. So 9 volts equals the current, which is what we're looking for, times 6. We divide both sides here by 6, and we end up getting that the current through the circuit is going to be 1.5 amps. From there, we can go ahead and find the voltage across the 4 ohm and the 2 ohm objects. Keeping in mind that 1.5 amps of current is going to leave the battery and go through both resistors here. So we can say V equals IR for each individual resistor. So it's going to be 1.5 volts times 4 ohms. So that means the 4 ohm buzzer gets 6 volts of resistance. And the 2 ohm light bulb, same thing, V equals IR, except now it'll be 1.5 amps times 2 ohms, and so we end up with 3 volts of current, or 3 volts across the 2 ohm resistor. All right, so let's move on to question 4 here. And so with this one, we're thinking about the current and voltage for these missing resistors, and we'll start with the current one. And keep in mind that the deal with current is current going into the junction is going to be equal to the current leaving the junction. So that's really what we want to think about when we're doing this problem. So I'm going to start right here with this junction. I see that 3 amps is going into that junction. I'm going to assume all the current is going clockwise. If you do counterclockwise, it doesn't really matter. You'll get the same answers here. So 3 amps goes in. 1 amp goes to the left here. That means the remaining current, which is 2 amps, must go to the right. The next one I'm going to do is this branch here. And so what I see here, there's not actually a junction, but I know that 4 amps of current is going down through this resistor. There's nowhere for it to split to, so all 4 amps must go through resistor C as well. So there are 2 of my answers. And then I'm going to think about all this current coming back together. The 4 amps, the 2 amps, the 1 amp. That's going to reform to create 7 amps of current, which is going to go up through here. And so that means that this first resistor will have 7 amps of current. For the second one, we're going to think about our rule for voltage. And so voltage is current. The deal is that every loop must add up to the voltage of the battery. That's our big idea for voltage. We also know that any resistors in parallel, like what we have right here, must have the same voltage. Okay, so I'm going to start by just filling in 5 volts for E. Then I'm going to think about some loops, so I'll start with this loop here. Okay, that needs to add up to 20, so I have 8 plus D plus 5 has got to be equal to 20, and so that means that D must be 7 volts here. And I can see here why that 5 volts has to be the same, because if I had taken this path, I'd need 5 volts here, all right, across this one, to make this loop add up to 20. The other loop that I can look at here is the one that goes all the way around the outside. And so I can say 8 plus 9 plus F equals 20. So then F is going to be 3 volts here. And so that's my answer for that one. All right, for this last one, we want to do a full circuit analysis of this particular circuit. So with this, we want to look for simple combinations of resistors, combine them, and slowly simplify the circuit. So first combination we're going to have is R3 and R4. Since they're in series, we're just going to add them, 9 plus 3. And so R3, 4 gives us 12 ohms. From there, we can go ahead and redraw our circuit here. And so we have 15 volts connected to R1 here, which is 1 ohm. Then we have R2, which is 6 ohms. And we just found that R34 is 12 ohms. So we can look for our next simple combination, which is going to be these two in parallel. Since they're connected in parallel, we do the 1 over RT equals 1 over 6 plus 1 over 12. I'm going to jump to solving this, but you could add those fractions and then, of course, use the x to the minus 1 button on your calculator to raise it to the negative first power and solve for RT. When you do that, you should find that the total resistance here is going to be 4 ohms. And so that's going to be 2, 3, 4 together. And so we'll do one last redraw of our circuit here. Here's R1, which is 1 ohm, connected to R2, 3, 4, which is 4 ohms. All right. And so what we can do then is get the total resistance here of the circuit, which is just 1 plus 4, or 5 ohms. So that actually answers question A, the total resistance of the circuit. For question B, we can go ahead and use Ohm's law, V equals IR. So 15 volts equals our current times our resistance of 5, which means our current is 3 amps. So that answers question B. Working our way back around to get the voltage and current on each individual resistor, we can say that that 3 amps goes through everything. So it's going to go to both of these. And then using Ohm's law, V equals IR, we can solve for the voltage. So 3 times 1, there's going to be 3 volts on R1. And 3 times 4, there's going to be 12 volts on R2, 3, 4. I'm going to off to the side here start writing these ones down because I do have R1 completed now. So for R1, I can say my voltage is 3 volts and my current is 3 amps. I'll do the same for R2 and then 3 and 4 as I get to them. So I'm going to focus then on this R2, 3, 4. That came from R2 in parallel with R3, 4. Since they were connected in parallel, each one gets 12 volts. And using Ohm's law, I can solve for the current. So 12 equals I times 6, which means this is going to be 2 amps. 12 equals I times 12, which means this is going to be 1 amp. All right, which makes sense because they add up to 3 amps as they should. I've now solved for R2. I know the voltage is 12 volts and the current is 2 amps. And now I can step this back one further here and finish up and get R3 and R4. So R3 and R4 were connected in series here, which means that each one of them will get this full current of 1 amp. And from there, I can use Ohm's law, V equals IR, to get the voltage. So 1 times 3 gives me 3 volts. 1 times 9 gives me 9 volts. And so I can fill in the rest of my chart here. And I'll zoom out so you can see the whole solution. R3 is going to be a voltage of 9 volts and a current of 1 amp. And R4 is going to be a voltage of 3 volts and a current of 1 amp. And there we have that full circuit analysis.